If you've been following the just incredible progress of large language models, we're living in an age of these architectural wonders. But here's the massive challenge, the one facing the entire field of AI. LLMs are trained once, they are huge, and they are brilliant, but after that initial training, they're fundamentally static.
Completely static, like a photograph.
Exactly. They're a snapshot of the world at one moment in time. They can do amazing things with what they already know, but they really, really struggle with true continuous learning. They're just not resilient to new info. They forget.
And that static nature, that's really the crux of the problem. We've sort of hit a wall where just making the model bigger or the data set bigger, it's giving us diminishing returns for things like adaptability.
Right. Our source material today introduces a really radical idea, nested learning, or NL. And this isn't just, a small tweak to a transformer block. It's a full reimagining.
Okay. NL frames these deep learning models not as just a stack of layers, but as a system of nested multi-level optimization problems. Each one is operating under its own set of rules.
I love that phrasing. So it's like an instruction manual for building dynamic systems, not just these static databases of knowledge.
That's a great way to put it.
So our mission today is, well, it's ambitious. We're going to unpack this architectural shift that NL is proposing. We'll see how it connects the mechanics of machine learning directly to neurophysiological principles.
Specifically brainwaves, how the brain uses different frequencies to consolidate memory.
And then we'll explore the continuous learning architecture that this allows us to build, which has the powerful name HPE. We're really diving deep into the next generation of AI design here.
Let's do it.
Okay, so let's start with the limitations of the current paradigm. For years, the mantra has just been more is better. Stack more layers for more capacity, more expressive power.
And it worked. For a while, it gave us fantastic performance on static in-distribution tasks.
But the sources we looked at, they point out 4 really serious issues that just scaling up doesn't solve.
Yeah, the core assumption that, computational power scales neatly with architectural depth turns out to be flawed.
How so?
Well, first, the effective computational depth doesn't always change, even if you tack on 100 more layers. And second, we're seeing that the capacity of some parameters, it just offers marginal improvement as the model gets deeper or wider. You're paying these huge costs for tiny, tiny gains.
And the other 2 problems feel even more critical because they're about the process of learning, not just the capacity of the model.
Precisely. The third one is that these models consistently converge to suboptimal solutions. We tend to blame the loss function for that, but the NL researchers, they argue the blame actually lies with our choice of optimizers. They're too primitive.
Okay, and the fourth, and this is the big one for continual learning, just stacking layers give you zero inherent ability to adapt fast to new tasks or take in new information without catastrophic forgetting. That inability to consolidate new knowledge. That brings us to maybe the most striking analogy in the research. The sources argue that current LLMs suffer from a pattern that's a lot like anterograde amnesia.
It's such a powerful metaphor because it just nails the exact failure mode. In the brain, anterograde amnesia means a person can't form new long-term memories after some kind of onset.
Right, but their old memories are still there.
Exactly. Their old memories are intact, so the person can function in the immediate present, but they can't consolidate any new experiences into their permanent knowledge base.
Like, how does that map onto an LLM after it's been pre-trained?
Well, the LLM's knowledge is split. It's got the immediate context, which is its short-term memory. That's the attention window where it's processing your current prompt. And then it has its deep pre-trained knowledge stored in those huge MLP layers. That's the long-past knowledge. But there is no effective process to move information from that short-term context into the long-term MLP knowledge.
So they can't consolidate.
They can't consolidate. They're perpetually stuck experiencing the immediate present as if it were always new.
Wow, that clarifies so much. It's why they can master some really complex tasks you give them in a prompt, but then they fail dramatically if you ask them to remember some new fact permanently.
Without a full, massively expensive retraining cycle, yes.
So if the problem is consolidation, nested learning must be the mechanism designed to fix it.
NL introduces that consolidation mechanism. It basically demands that we stop looking at the model as this single uniform thing. Instead, we have to represent it as a set of nested multi-level optimization problems. Each level in that hierarchy has to learn to compress its own context flow.
And this is where they pull directly from neuropsychology, right? NL grounds its whole approach in this distinction between memory and learning, all rooted in associative memory.
Exactly. In this framework, memory is just. It's a neural update caused by an input. Every single time a weight changes, that's a memory.
Okay, a simple update is a memory.
But learning is the organized process for acquiring effective and useful memory. So this means that in the NL world, every single component, a network block, an optimizer, everything has to be treated as an associative memory system, a function that takes in keys and produces values by compressing its context.
This is where it gets really compelling for me, that direct biological parallel. The brain uses brain oscillations, delta, theta, alpha, beta, gamma waves.
Yeah, all those different frequencies.
Right, from
Yeah.
like 0.5 hertz up to 100 hertz.
Yeah.
And the critical part is the brain doesn't have a central clock. It uses these different frequencies to manage plasticity and memory consolidation across totally different timescales.
And NL directly mirrors this. It's a multi-timescale update system. It says that parameters in different levels of the model have to be updated with their own specific mandated frequency.
Okay, so what does that actually let the model do?
Well, it allows parameters that are dealing with immediate input, like processing tokens, to update really quickly. Those are the high-frequency cycles. While the parameters that are tasked with consolidating deep, abstract knowledge, they integrate information over much longer, slower cycles.
So NL isn't just about what the layers do, but when they're allowed to change. It's like mandatory time scheduling for the parameters. And that's formalized in their ordering principle.
That's it. The ordering principle dictates a strict, transparent hierarchy. You order components into levels based on their update frequency. The higher the level in the hierarchy, the lower its required frequency.
And that structure is what keeps them from interfering with each other.
Exactly. It mandates an exclusive gradient flow for each component. They can't mess with each other's optimization problem, which ensures they optimize their own unique context over their assigned timescale.
But doesn't introducing all these different strict update frequencies just make the model vastly harder to train and debug? I mean, we're trading the simplicity of one global learning rate for this huge array of internal timers.
Well, it's a necessary trade-off. It's a trade-off for getting continual learning. Simplicity in the architecture, like a standard transformer, that leads to amnesia.
Okay.
The complexity in the dynamics of the architecture, which is what NL is all about, that's what allows for adaptation. And the brilliance here is that by making the internal dynamics explicit, NL shifts the optimization problem. You're no longer just finding the best set of static weights.
You're finding.
You're finding the best set of learning rates and scheduling rules for those weights. It forces you to build systems that learn how to learn. That is a profound shift in perspective. And the first huge breakthrough NL gives us is this mathematical white box insight into something we use every day, the optimizer.
Right.
I mean, the standard gradient-based optimizers, atom, SGD with momentum, we've always just treated them as these simple numerical update rules.
Yeah, black boxes.
NL proves they are, in fact, inherently associative memory modules that are designed to compress the stream of gradients they receive.
Wait, hold on. That's not just a cute analogy. You're saying that changes everything about how we debug a training run. The optimizers we've been using are, mathematically, just basic memory systems for gradients.
Absolutely. Let's take a classic momentum gradient descent. NL decomposes this into a two-level optimization process. The outer level optimizes the slow weight, that's the actual network parameter, W.
Okay.
But the inner level, it optimizes the momentum term, M, and that M term is now understood as a keyless associative memory. Its whole job is to store and compress past gradients. It's a fast network that generates weight updates for this whole network.
So if traditional momentum is basically just a simple linear average of past gradients, I can see why it struggles. It's like averaging the last 10 days of the stock market. You get a rough direction, maybe, but you miss all the subtle changes in the trend.
That's a perfect analogy because that traditional momentum memory is linear. Its expressive power is really limited. But if we recognize it's a memory module, we can start designing deep optimizers with way more capacity.
How do you make an optimizer deep?
You replace the simple linear memory in the momentum term with a fully persistent learning module, like a small MLP, a multi-layer perceptron.
Ah.
This gives you deep momentum gradient descent, or DMGD. Now, the momentum itself is a miniature neural network. It has a massive capacity to capture complex gradient dynamics, not just their average. It goes from averaging the trend to learning the pattern of the trend, which allows it to better predict where the update should go next.
That's a complete redesign of the training process itself. And NL also lets us re-examine other key architectural components like attention and transformers.
It does. NL shows that even a simple linear attention model trained with gradient descent is inherently a two-level optimization problem.
Okay, so break that down.
The slower outer loop optimizes the projection layers, your Q, K, and V weights. They define the high-level representation space.
Right.
But the faster inner loop is dedicated to optimizing the memory matrix M, which is where the recurrence and immediate knowledge storage happens. And during that fast inner loop, the projection weights are held frozen. NL gives us the mathematical assurance that each part is doing its assigned job on its correct timescale. This systematic approach of decomposing and defining optimization problems by frequency, this leads us directly to the solution for that anterograde amnesia problem. So tell us about the full architecture NL enables the Continuum Memory System, or CMS, and this OP module. The Continuum Memory System, or CMS, is the generalized solution for perpetual consolidation. It takes our traditional view of memory, short-term attention and long-term FFN layers, and just expands it. CMS is a chain of specialized MLP blocks where each block is explicitly associated with a different update frequency and a specific chunk size.
So the chunk size,
Yeah.
that defines how often it's allowed to consolidate information.
Correct. The parameters of a given block only update every, say, C,000 steps. And those parameters are explicitly responsible for compressing the context flow they received over that specific chunk length into abstract, durable knowledge.
So a regular transformer FFN is just a special case of this.
It's a special case where C is basically infinite, meaning it only updates once during that massive pre-training run.
So instead of a single static brain, HOPE essentially has multiple brains running at different speeds, each consolidating different kinds of information. It sounds like a really sophisticated tiered storage system.
Yeah, it's an excellent analogy. Hope the architecture that comes out of this combines this CMS with its low, mid, and high-frequency FFNs with an underlying sequence model called self-modifying titans, which can even learn its own update algorithm.
Can you give us a sense of the scale of those different speeds? You said low, mid, and high frequency.
Yeah, so in the examples they give, the low-frequency FFNs are set to update only every 16 million steps. That's the massive, slow archival hard drive, storing generalized knowledge that barely ever changes. The mid-frequency FFNs might update every 1 million steps. And then you have the high-frequency FFNs maybe updating every 16 steps.
Acting as the super fast cat.
Exactly, for immediate skill acquisition and local context. It's an artificial brainwave system that achieves dynamic memory processing.
So by injecting this mandatory scheduling based on neuroscience, what kind of performance improvements do we actually see? I mean, does this complexity pay off?
Oh, it absolutely does. When you compare models of roughly the same size, around 1.3 billion parameters, Hope achieved a really strong average accuracy of 57.23% across the language and reasoning tasks they tested.
And how did that compare to a standard transformer?
It outperformed the equivalent static transformer plus model, which scored 52.25%, and it also surpassed modern recurrent models like RetNet and DeltaNet. The system is just demonstrably more effective because of that continuous learning.
The performance increase really suggests that shifting focus from just simple capacity scaling to defining the complex internal dynamics. That's the next crucial step. The solution to the amnesia wasn't a bigger chip, it was a better clock.
Precisely. The core takeaway of nested learning is that it fundamentally changes the definition of deep learning. It shifts the focus from just stacking components to rigorously defining the internal dynamics and the context flows within the architecture. It treats the design of the learning system itself as an incredibly complex optimization problem, and ultimately, NL gives us the why behind one of the most mysterious capabilities of modern AI in context learning.
Right. It explains that the in-context learning we see emerge in these huge models, it actually arises directly from the system's ability to compress its own context flow effectively. And it gives us the mathematical framework to understand that and to engineer it intentionally instead of just hoping it pops out through sheer scale. That leaves us with a pretty provocative thought building on this whole discussion. We've established that traditional optimizers, like momentum, are fundamentally memory modules optimizing gradients. So if the best path forward for powerful continual AI involves designing these deep optimizers, which are complex neural networks in their own right, designed to learn their own training dynamics, what does that imply? What are the implications for how we understand, debug, and ultimately trust the training process in future AI systems?
Yeah, the complexity is moving from the data into the very mechanism that learns.
Will we even know how our AI learned its skills if its learning mechanism is itself a complex, self-modifying network? Something to think about as you watch the next generation models evolve.